So, on Thursday and Friday, we were talking about these distributions that are normal. Okay, so all these questions, I don't know if this has ever came to your mind when you're seeing things like this. I always thought, you know, when they would give me in like an algebra class, they would say, this scenario follows this formula or this equation. And I would be like, okay, well, whatever, but how do I know that? Who knows that that came out that way or that does it that way? So there's always basis behind those types of things. And so when you guys see that it says in all these questions, you see there an example. It says, some doctors believe that a person can lose 5 pounds on average in a month by reducing his or her fat intake and by exercising consistently. Suppose weight loss has a normal distribution. Well, do I just go throughout all of these questions with this assumption that things are normal, or is there like a legit way of deciphering whether something is normal?
Sammy Bodecker at the end of the period, he's got a problem then with putting him on the spot on the board. He wanted it last week. He's going to be careful what you wish for, big boy. All right. Put him on the spot.
All right. So we don't want to march through the entire course just making all these assumptions and not really know whether these assumptions are accurate or not. So when you guys, if you were to do this on your own, if you were to do a survey and collect this data, okay, do a study, collect all this data, you would run that data through testing, okay, that would analyze whether your data is normal or not. So let me see, I closed it on accident, but I'll see if I can open it back up. All right, so if we collected our data and took that data and organized it graphically, okay, as a histogram, we could maybe realize that we could fit a curve to that histogram, right? All right, so this curve would fit that histogram, and we could argue that this is somewhat maybe normal, okay? And there are, you know, if we look at any situation, no situation is going to be absolutely normal, okay? So there's a little bit of leeway with that, but this is a symmetric distribution, so we're going to say it's going to be normal. Now, if the issue with histograms and letting these visual tools help in deciding whether something is normal or not, we could change the bin width, okay, which would be the width of each one of these rectangles. And if we change it, so right now they're looks like they're like a width of 2 or 2-ish. If we change them to like 5, it's not going to look the same. Okay, it might look a little bit less normal. Does that kind of make sense? I think the narrower the width of your rectangles, the better argument you can make for it being normal. Here's a situation where you know, that does not necessarily fit a normal looking distribution, right? Okay. We have this one here. Obviously, again, not so normal. Not normal. Okay, but now these are some visuals, and this again is the same idea. Instead of using the histogram, we're just using the curve here, the density curve. So the visual might not be all that great, okay, but there is something called a QQ plot, okay, which talks about confidence intervals, and we'll talk about confidence intervals in a couple weeks. Basically what here is that we and we'll talk about how we develop this line eventually, is if you plot your line and then you plot your data around that line, okay, or just plot your data and it follows that line and it's within the, we call these confidence bands. If it's within those confidence bands, then the argument is that the data was normal, okay? Basically, then when we plot that data in a histogram, it's going to be symmetric for us. Now, all your visual techniques might lend to fit, so this one does not necessarily do that, so we would not argue that this one would be normal. That can be an issue, okay? And this will be something that we get into. I don't know if we'll talk specifically about the Shapiro-Wilks test, but you will learn how to do what we call hypothesis testing, okay? Which basically you create a hypothesis, which is, you guys know what hypotheses are from, or hypotheses are from, like a science class, right? Yeah. Okay, so we create, what we call a hypothesis that the data do not follow a normal distribution, okay? And then we create what we call a null hypothesis, which says the data does follow a normal distribution. And then we run through what we call, in this case, the Shapiro-Wilks test. So we'll do some calculations. And the results that it gives us, okay, will tell us whether we accept this hypothesis or we reject it. And if we reject our hypothesis, then we accept the null hypothesis, and it tells us that the data does follow a normal distribution, okay? But there are formulas in probabilities that we work through in order to do this, okay? My argument here, and whether we get this involved in this elementary stats class to be able to do this, it just depends on the time that we have. But all of this procedure is what takes place before somebody writes a question like this that says, where'd it go? Suppose the weight loss has a normal distribution. They've already done the preliminary work to know that the data follows that type of curve. Does that kind of make sense? I just want to make sure that you don't just think, well, this is just a bunch of bogus stuff that we're just making these assumptions that we can't really validate one way or another. Okay. Question?
When you copied, like, whatever, why didn't I give you an option to tweet that?
Excuse me?
Like, when you like, highlighted something, it gave you an option to tweet it?
I don't know. I can see that.
Can you tweet it real quick?
No, I'm good. Okay, so let's get into working with the normal distribution. Just basically today, analyzing z-scores, seeing where they fall on the normal curve. Remember what this says here. It says suppose that x, which is your random variable, okay, and it's continuous. So x has the distribution or takes on the distribution that is normal with, does anybody remember what that first one is? What that 5 represents? The 5 is mu, and the 6 is the standard deviation. The way I remember that is M and S are alphabetical. Mu and standard deviation are alphabetical, right? So mu comes first, okay? So suppose x is 17, find the z-score, okay? So really what we got going on right now is if I'm looking at the current situation where it's saying mu is 5 and one standard deviation is 6, that's going to put us out here to 11 and then out here to 17. Does that make sense? They want us to determine what is the z-score that goes to 17. So if I were to take this normal distribution and standardize it so that mu becomes 0 and a standard deviation becomes 1, where is this 17 going to go to? My hope is that you can see that right here, we added one standard deviation to get to 11, right? We added a second standard deviation to get to 17, correct? So what should, if that's one standard deviation on the standard curve, then this would be 2 standard deviations. So that 17 should match up to a 2. Does that make sense? Okay, now I want to go through the formula to make sure that that kind of pans out. The formula for finding the z-score is x minus mu divided by the standard deviation. Is everybody okay with that? Now, x for us is our specific data point. So we take 17 minus mu is 5, divided by a standard deviation of 6. Does that give you 12 over 6? Does that give you the 2 that we said that 17 should go to? And the reason we want to do that is I might have interest in whatever the context of this problem is, knowing what is the probability of getting a z-score or a specific data value that is less than 17. In order to do that, to find that probability, I need calculus. Okay? But if I standardize it and I want to know what is the probability of getting a z-score that is less than 2, okay? Does anybody remember the empirical rule? What the idea was of standard deviations of 2? How much area is between 2 standard deviations of the mean? There's 95, right? Okay. And now if I just say less than 2, well, now I'm also going to incorporate this area down here. Okay, so this is actually going to go not to 95, but 97.5 because of that lower 2.5% that I can incorporate. So the question, let's say that maybe we take a test that is out of 20 points. Okay, that test has a 20 points. Let's say, yeah, let's do 20 points. So let's say that test has a mean of 5, standard deviation 6. Okay, so the average score is 5. Correct answer. Okay, standard deviation 6. So, in my practice, if I would see that, we would probably have to talk about, how did we teach that? Okay, and what were the issues that everybody got an average of 5 on? But the question would be then, okay, somebody that, if we score 17, what's the probability that somebody scored less than or equal to 17? That probability would be 97.5. What's the probability of somebody scoring over 17 would be the complement of that, 2.5. Does that kind of make sense? And that would be the benefit of being able to standardize a z-score or a data point to get a z-score. Okay, now if I ask for what is the z-score for x equaling 1, okay, so we have this exam, we had 5 was the mean, somebody scored a 1 on it, okay, so we go z-score is x minus mu over sigma, so our particular x in this case would be 1 minus 5 over 6, so it's going to give me what, negative 2/3, negative 4/6 reduced. So that tells me then that this person, because the z-score is negative, this person did less than the average, right? They're below the average. Now, they're not that far below the average. I mean, it's less than 1 standard deviation away. Okay? So, if that's negative 2/3, okay, it's still within that 68% section around the mean. Okay, but there's 2 ideas here that we're trying to calculate. Can I find the z-score? Is everybody okay finding the z-score? And then when we place that into the standard curve, what is that z-score telling us? Okay, if it's to the left of the mean, we're less than the average. If it's above the mean, we're better than the average. And then we can start to decipher, okay, probabilities of that are associated with those locations. All right. So this next example, that obviously that didn't have any context to it. This example does have some context. We've got doctors that believe a person can lose 5 pounds on average in a month by reducing fat intake and exercise. Okay. So suppose weight loss has a normal distribution. Okay. Let x equal the number of weight lost in pounds. Yeah, bad color. By a person in a month. Okay, it says use standard deviation of 2 pounds. Okay, so we're going to rewrite that in this notation. It says our random variable has the distribution that is normal with a mean of 5 and a standard deviation of 2. The reason I show this question is because I want to make sure that we understand how, when we write the random variable in words, how we then write and kind of conduct ourselves through the algebra of a particular situation, okay? Because the way we wrote the random variable in words that we were losing weight, right? When you see the word lost, what operation do you attach that to? You think subtraction, right? You think negative values, correct? But because we wrote the random variable of weight lost, and this also matches up to lost, then this 10 pounds is actually going to be a positive number because they match. Does that make sense? Okay. When we say that they gained 3 pounds, how does gained compare with lost?
It's bad.
It's bad compared to lost, right? So that would be the negative. So when we do the z-score down here for 3 pounds, that x value is going to be a negative 3. This x value is a positive 10. Is that okay with everybody? That's important to justify. So if I want to find z, again, it's x minus mu over sigma. So x is 10 minus mu, which we said was 5. Sigma is 2. Gives us 5 halves or 2.5, right? Okay. Now, why would I want to know this? Well, if I go to my normal curve, my standardized curve, if mu is 0, and there's one standard deviation, there's two standard deviations, here's a third standard deviation. Right now, our data point is lying right there, correct? Would you guys agree that there is a lot of area to the left of that? Would you guys agree that there's very little area to the right of it? Okay, so the probability of losing 10 pounds is very, very, very slim. Okay, it's greater than 2 standard deviations away from the mean, which 2 standard deviations away from the mean, so let's say that's 2 standard deviations to the left, and this would be 2 to the right. That area right there in itself is 95%. Does that make sense? If I cover this in, okay, that's the lower 2.5%. So now we're looking at 97.5%. Okay, so, and there's some area right here as well that we would need to add in. I don't know how much that is, but this is greater than a 2.5 z-score is greater than more than 97.5% of our data. So that would be considered an unusual amount of weight loss. Okay, we've talked about, I explained to you that my wife works with speech therapy. One of her areas of speech is putting people on diets. Okay, for usually when people have stroke or a stroke, they have swallowing issues. Okay, I think it's called dysphagia, where they just can't eat their food and they choke and they get pneumonia and that kind of stuff, and then obviously that can turn into death. So she will decide whether to give them like soft foods, or like sometimes I think they're called like mechanical soft. So they basically take your hamburger and they put it in a blender and make it something you can suck through a straw. Okay, or they take it and make it into like hamburger helper. Okay, so it's just easier for the person to chew and swallow, because if they can't eat, they're going to lose weight and they're going to get in a worse condition, right? So what she does is she will measure through like monitoring them, like what kind of diet can I put them on. And one of the things that they look at, that nurses will look at, is they'll monitor their weight. They'll weigh these people every day, and they'll start to look at, they're losing weight rapidly, or maybe they're gaining weight rapidly, and that can then signify or identify to my wife that we need to look at this person, evaluate them, and see if we need to change their diet, if we need to put them on like supplements, that kind of thing. Does that kind of make sense? So if somebody was in this 2.5, okay, within a month, a z-score 2.5, that's going to be an identifier. Get this person on a plan, do some type of treatment with them, because they're unusual in regards to their weight loss. Okay. Here it says, suppose a person gained 3 pounds, find that z-score. So again, okay, so x is now, like we said, gained was the opposite of lost, so that's where we're going to look at -3 as being the x value. Minus the mean, which is 5, and we'll divide by 2. So this puts the person at -4, right? Okay. Again, so, if we're trying to diet, and we put somebody on a diet, and we put them on an exercise routine, and they've gained 3 pounds, that puts them 4 standard deviations below the mean. That is an abnormal z-score. Okay, it's very, very low. If we look at the, let's see here. I want GeoGebra. So if we go to -4, okay, you can start to see the area that is shaded in here, right? It is everything that's left of -4. It's a very, very small area, which is where you're seeing this number right here, okay, which is a 0.40 and then a 316. That's the probability that if put on this diet and exercise regimen, that they would gain 3 pounds. Okay, that's kind of the way Mr. Fay diets. Let's see here.
That's all I got.
Yeah, I can diet for about a week, and then I just start eating everything I didn't eat that week in like a day. All right, so here's the rule that we've been talking about in the past. Now, it's not; these are all approximations, okay? Because if I talk about the region between 1 standard deviation below the mean and 1 standard deviation above the mean, okay, that was the 68%. But if we go back to the calculus that generates that 68%, it's not on the dot 68%. If I go between -1 and 1, you see that that percent is actually, come on, 0.682689. So it's an approximation when we say 68. We just round it, okay? And I would argue that the reason we can do that, we can round it to 68, one, we're saying about, but two, is that no population is ever exactly normal. So we're already kind of taking some liberties with that. So there's nothing wrong with taking some liberties here, okay? But it's good enough, especially if our data is from a large enough sample, those rounding issues are not a big deal. So that's 68%. The next one is 2 standard deviations, which again is not exactly 95. I believe it's 95, like 0.44, something like that. Yeah, 95.44997. Round it to 95. And then if we go 3 standard deviations, (99.73). That's the one that's about the best in regards to precision that the rule uses. And that's, I mean, you look at the shaded regions here. Okay, all of that there would be then the 99.7. Something we can do, so if this is 68%, a lot of times then we're going to refer to this as the lower 16%. And this would be the upper 16%. And the reason we can do that is because it's symmetric. So if we've got 68 out of 100, that means there's 32% left over, right? 32% divided by 2 gives me 16. So that's where I get the lower 16 and upper 16. Here, this is the one that we'll use the most. Okay, a lot of our confidence intervals are targeting these two, 95 and 99.7. This one here, this would be so we got 5% left over outside these 2 standard deviations. So this would be the lower 2.5%, and this would be the upper 2.5%. And those are some values that we'll need to kind of acquire if they ask us, what's the probability that X is less than a Z-score, and actually I don't want to use X, I'll use Z. What's the probability that our Z-score is less than 2? Well, less than 2 would incorporate that lower 2.5, right? And it would incorporate this 95, so the answer to that would be 97.5. Does that make sense? Okay, so the empirical rule tells us, how our data aligns on both sides of the mean, okay? But we might have to do a little bit of arithmetic if I'm just looking at, if I find one Z-score and ask, okay, what is the probability of everything to the left of that Z-score, or how much area is to the left of that Z-score, or how much area is to the right of that Z-score, okay? And there will also be times, well, what if I want to know what is the area between those 2 Z-scores? -1 standard deviation to the left and 2 standard deviations to the right. So we'll talk about how we'll have to use our tables to do that, but what would be that shaded area there? Okay. Normally when we talk about z-scores, again, we're not, and we talked about this 2-3 days ago, we're going to be interested in our values falling within an interval. Okay. So we won't say what's the probability of a z-score of like 2. Because if you remember, we talked about the width of that rectangle essentially when we do the integral at 2 being 0, so there would be no area associated with that. So what we'll do is say what's the z-score associated with z values of less than 2, or between 1.9 and 2.1 or something like that. Okay. This example says the mean height of 15 to 18-year-old males from Chile was 170 in 2009-2010 with a standard deviation of 6.28. So again, these are things we can determine. We spent most of chapter 1 and 2 taking data, raw data, determine what the mean and the standard deviation from that raw data is, running through formulas. So we can do those two things. Okay. It says male heights are known to follow a normal distribution. It says let X equal the height of 15 to 18-year-old males from Chile in 2009 to 2010. Therefore, your random variable will have the distribution that is normal with a mean of 170 and a standard deviation of 6.28. Okay, so this asks you, okay, if you have a person that's 168, find the z-score that is associated with them. Say again? Okay. So if I got X, so X is that one particular value. So 168 minus mu, which is 170, divided by, what was it, 6.28? Gives us negative 0.318471338. We'll talk about maybe the need for rounding later on. But that's the z-score associated with the 168. Now, what's that z-score tell us? If it's negative, it tells us what? It's below the mean. Okay, so this person is shorter than 170. We knew that, right? But is that unusual? If we're talking about, so if we've got so negative 2 to positive 2, okay, and we're at negative 0.3, so we're kind of where my cursor is right now, okay, is that pretty close to the mean? So it's not, they're not an oddity, right? Does that make sense? Okay, now if we said that this person was like, let's say that we do a z-score where the person is like 110 centimeters, divided by 6.28. Okay, so 110 minus 170 is negative 60, divided then by 6.28. So now that's negative 9.55. They are 9.5 standard deviations below the mean. So that person would be, I can't even zoom out that far, but that person would be, that's negative 4 standard deviations below the mean, right? They would be even further. Would that person be considered an oddity? Yes. Okay. So that's, it allows us to identify maybe whether somebody is an outlier in a population or not. Okay. Let me get out of here. Let's do this next. We'll skip this one. This is doing the exact same thing. Okay. Actually, no, it's not. Let's do this one. Here it tells you the z-score. Okay, so suppose that the height of a 15, 18-year-old male from Chile, 2009-2010, has a z-score of 1.27. If that z-score, well, first of all, what does that z-score tell you? It's 1.27. It's above the mean. Okay, the mean was 170. I think the standard deviation was like 6.28. So this person is going to be above like 176 centimeters. Okay, but let's find exactly what they are. So our z-score is found by taking x minus mu over standard deviation, right? So in this particular situation, I'm not trying to find Z. I know that. I'm trying to find X. So I like to, because we don't see these types of questions enough to really learn the other formula. I just like to plug in the things I know. So Z is 1.27. I don't know X. I do know mu is 170. And my standard deviation is 6.28. So what would you do now to solve for X? Yeah, multiply by 6.28, right? So it gives me 7.9756 is equal to X minus 170. Add to 170. So now I'd have 177.9756 is that person's individual height. Okay, which we said should be, because the one standard deviation was 6.28 above 170. So that'd be 176.28. 1.27 is a little bit more than that, a little bit more than one standard deviation. So that 177.9 number makes sense, right? Okay. Now, if you had to do, like if I said, okay, what's a z-score? What's the height of a z-score of 1.27? What's the height attached to a z-score of 1.37, 1.47, 1.5? If you had to do that over and over and over again, it probably makes more sense to take this formula here and rewrite it as z times sigma plus mu is equal to x. Okay? The z-score, so remember what ours, and this should make sense, our z-scores, we want them to be, like, if it's 0, if our z-score is 0, I got 0 times sigma, which is 0, plus mu, would equal to that. So that would tell me if our z-score is 0, then the data value that I'm looking at is my mean. If z-score is 1, okay, then I have one standard deviation plus my mean, right? So this is setting up essentially this image here where I've got my mean plus one standard deviation would put me right here, plus two standard deviations put me there, plus three standard deviations put me there. Does that kind of make sense? They might ask you, this should not be too difficult. Provide a range of values, which 68% of your data should exist. So the range of data for 68% is one standard deviation to the right and left of the mean. 95 is two standard deviations to the right and left of the mean. And 99.7 is adding or subtracting three standard deviations. So if I want to go, if 50 is my mean and 6 is my standard deviation, I'm going to go 50 plus or minus 6. And then that range of data would be what, 44 to 56. And then here I would go 50 plus or minus 12. So that's going to be 38 to 62. And then the next one would be 50 plus or minus 18. So we'd be looking at 68 less than x, and then this would be 32. And the idea is eventually we're going to talk about confidence intervals. And if I have a population of people, let's say you guys are a population, I'm talking about their heights, and I pull out Lucas, and I don't know his height yet, I could maybe say I am more confident that his height is going to fall in the range of 32 to 68 than I would be by saying his height is going to fall in 44 to 57 or 56. Does that make sense? Because that band of values is a lot wider when it's 3 standard deviations than the band of values when it's 1 standard deviation. Does that make sense? So we'll talk about how z-scores help eventually with us determining confidence intervals, which is basically saying how confident you are in your data, okay, your arguments you're making off your data. We'll pick up over there tomorrow. Hopefully by the time you guys get here, your computer issues are all resolved.